Here's an example of a physics problem that involves relative motion in 2 dimensions. You wish to row straight across a 63-meter wide river. You can row at a steady 1.3 meter per second pace, and the river is flowing at 0.57 meters per second. And the question is, what direction should you head in order to go straight across, and how long will it take you to cross the river? Let's make a sketch of the vectors, the velocity vectors involved in this problem. Here I've drawn them here, and we can go through what each of the notations mean. So, for example, we have the velocity of the rower with respect to the shore, the velocity of the water with respect to the shore, and the velocity of the rower with respect to the water. So you can see that we like to head straight across. This would be us with respect to the shore, but we're going to have to row a little bit off into the current so that the resultant velocity or motion is straight across. So what's good about drawing this graphical picture is we can now see how these vectors are related to one another. If you can imagine, we're going to add head to tail to get the total resultant vector. The velocity of the rower with respect to the shore is the vector sum of the velocity of the rower with respect to the water and the velocity of the water with respect to the shore, the current. And there's kind of a neat notation here. You can see that the water indice here and to kind of cancel to give you the rower with respect to shore. Now, in order to solve this problem, this relationship, of course, is a vector relationship, and it really represents two relationships, the relationship between the different components of this vector. So to solve this problem, we were going to have to write down those two relationships between the components of the vector in this two-dimensional problem. So to do that, I'm going to go ahead and define an x and a y axis. We'll take this straight across direction to be in the y direction, and the horizontal direction we'll call x. So given that coordinate system, we can write down the x component of this vector equation. So the x component of the velocity vector rs is simply 0. The x component of the velocity vector r rower with respect to the water, we'll need to use this angle theta. And the x component of this vector, which will be along this direction, of course, is opposite over hypotenuse, so we use the sine function. And then finally, the x component of the current, the water with respect to the shore, is just this full magnitude. The y component of this vector equation, the y component of VRS is the full magnitude, VRS. The y component of the vector rower with this velocity of the rower with respect to the water is going to be the component of this vector along this direction, along the y direction. And you can see this is the adjacent of the hypotenuse. So we have the magnitude v of the rower in the water multiplied times the cosine. And then finally, the y component of the current here is 0. The current is all in the x direction. So now we have two equations and we're able to solve the problem. Our first question is, what direction should we take? So we want to solve for theta. Let's use the x component equation to solve for theta. We'll just rearrange this, isolating and solving for sine theta. Doing that, we get this expression. It's the ratio of these two magnitudes, the velocity of the current over the velocity you can row with respect to the water. And that's just these two values here, 0.57 over 1.3. And if you plug that into your calculator to get the inverse of the sine, you'll find a quantity of 26 degrees. The next thing we want to do is figure out how long it will take you to cross the river. So the time it takes you to row across the river is just going to be equal to the distance you have to go divided by your velocity. So we know the distance to be 63 meters, and the velocity of the rower with respect to the shore we can get from our y equation. And you can see I'm going to substitute in the values of how fast you can row with respect to the water times the cosine of the angle we just derived, which is 26 degrees. So putting in those values, plugging them into the calculator, I get a time of 54 seconds. Now, this seems pretty reasonable for a rower going at about a meter per second, going 60 meters. That might take about 54 seconds, just under a minute. So here in this problem, we've used a couple of different math skills. Certainly we've used some trig to find the components of the vectors, and that was an important math skill. We've also had two component equations, and we had to solve these equations to isolate quantities and get values for individual variables. We did this twice. And then finally, we got a little bit of practice in understanding vectors in the sense of this was really physics involved a vector sum, and being able to do that algebraically as well as pictorially was a useful skill. So if you want to practice those math skills, jump into the modules and then come on back and do the do-it-yourself problem.